bane of my existence. Yeah, thank you, Emily. Please take it away.
Okay, so as Yossi said, I'm going to tell you about A-polynomials of knots that are related by Dehn filling, and particularly about how we can simplify those equations and calculations. So the first part of the talk, I will introduce you to the A-polynomial, and then after that, I'll talk a bit more about computing these things. So let's start with what is the A-polynomial? So basically, this is a knot invariant that was introduced in 1994 by Cooper, Culler, Gillet, Long, and Shalin. They were interested in the character variety of the fundamental group. And basically what they get is a polynomial in two variables, L and M. We use L and M because they're coming from the longitude and the meridian of the knot. And it defines a curve in C cross C. So I'm not going to go into the details of this, the definition today, because I don't think it's particularly enlightening. But I will say more about the calculation, obviously. And just as an example, to give you a flavor of these things, this is the A-polynomial for the figure 8 knot. And so these things can get quite big and ugly very quickly. So let me tell you about one of the really interesting results about the A-polynomial that might get you a little bit interested. So the result can be sort of referred to as this boundary slopes theorem, which basically refers to two different notions of a boundary slope. So the first notion of a boundary slope, I want this on the screen as well, is that of the Newton polygon. So you can talk about the Newton polygon of any two variable polynomial. Basically what we do is we look at this sort of lattice of the coefficients. So let me fill this in. So for the figure 8 knot, we can take all of these terms and put them into this grid. So the first term is m to the 4. So we put in its coefficient here. Then we get a minus L, and then we get a plus L m squared, plus 2 L m to the 4, plus L m to the 6, minus L m to the 8, and plus L squared m to the 4. Okay, and so once we've done that, we just sort of look at where all of these non-zero coefficients are, and they're sort of in this, we give a point for everyone, and they're in this layout here, and then we take the convex hull of this thing, and we get this polygon. And so this is the first notion of a boundary slope. So we can look at the slopes of these boundary edges. And in this case, they are plus and minus 4. Now, the second notion of a boundary slope is in the knot complement. So we can look at the knot. So this is the figure 8 knot in orange. And so in the complement, we look at these two slopes, the meridian and the longitude. I've drawn these extra couple of twists here because this is the preferred longitude. So it's the unique curve on the boundary torus that bounds a disk inside the knot complement. And so we can talk about slopes on the boundary torus in terms of these generators. And so what this result is saying is that the slopes of the Newton polygon are actually slopes that bound incompressible surfaces inside the knot complement. So in this case, if we took 4 laps around the meridian and 1 lap around the longitude in either direction, that curve on the boundary of this torus bounds a incompressible surface inside the knot complement. So this is a pretty profound result. It's not at all obvious why it's true. We've sort of taken this polynomial seems kind of arbitrary, like where its coefficients are in this grid, and somehow that's detecting incompressible surfaces in the knot complement. So I just wanted to highlight this because it's maybe one of the best ways to get people interested in the A-polynomial. And now I'm going to tell you a bit more about calculating these things. Okay. So unfortunately, calculating A-polynomials in general is a hard thing to do. So it all basically comes down to this problem that we're trying to solve a polynomial system of equations. So basically, all of the most direct methods for computing A-polynomials boil down to you sort of come up with a system of polynomial equations in lots of variables. So you'll have the variables L and M and then a bunch of other ones. And essentially you want to eliminate all the other variables to get a polynomial in L and M. And this is just still not particularly well executed by computers. There's not really effective algorithms that do this if your system is too big or your degrees of the polynomials are too high. So let's look at what we do know. So let me summarize sort of what knots we do know the A-polynomials for, and then I'll talk a bit more about how we calculate them. So A-polynomials are known for knots with small crossing numbers. And the reason for this is basically you can get this system of polynomial equations, you can get essentially one, or I think it's technically 4 equations per crossing. This is because you can come up with the Wirtinger presentation of the knot of the fundamental group. And basically your system of equations comes from making sure that the relations hold. And so as you get more crossings, you get many more equations, and that makes it hard to calculate. And when I say small crossing numbers, I mean, we know the A-polynomials of all knots with up to 8 crossings, most of the knots with 9 crossings, and many of the knots with 10 crossings, but not all. Then the next class we have is knots that have low triangulation complexity. And so this might seem a little bit out of left field at the moment. I'll make it a bit clearer why triangulation complexity is relevant in a moment. And when I say low triangulation complexity, I mean we know A-polynomials for all hyperbolic knots that can be triangulated by up to 7 ideal tetrahedra. And so this work is all done by color, basically. So Mark Color has a numerical method for calculating A-polynomials, and he's got a website where he lists all of these. So we also have formulas for some families of knots. So when we have a particularly nice sort of group presentation, or there's some other strategy that people can use, we've got some formulas. So the torus knots were known to Cooper, Color, Gillet, Long and Shalin in their original paper. That's a pretty nice, simple group presentation, so it works nicely. Twist knots, originally Hosty and Shanahan came up with a recursive formula for the A-polynomials of twist knots, and Dan Mathews then made that formula explicit. We know A-polynomials for some two-bridge knots. These are due to Ham and Lee and also Peterson. And these two-bridge knots and pretzel knots, these are recursive formulae. So the pretzel knots, Garufalides, Mattman, Tamura, Yokota all have these results. And then I just say a handful of others. I know there's at least one other paper, so me and Zhang came up with explicit formulas for iterated torus knots. And I am willing to believe that maybe I've missed something, but basically this is everything that's out there. Okay, so let me tell you a little bit more about why triangulation complexity is relevant. So Champanica is sort of responsible for this idea. So in his PhD thesis in 2003, he developed this method for computing a similar polynomial, let's say. So basically, he was looking at hyperbolic knots and considering their gluing variety. So if you have a hyperbolic knot, you can take an ideal triangulation of it, and then you get all this gluing information about how those tetrahedra glue together. And this basically gives you a system of polynomial equations. And then you're using information about the meridian and longitude to get your variables L and M, and now you have this system of polynomial equations that you want to eliminate all your variables except the L and M to get the A-polynomial. And it's not technically the A-polynomial. What you get is very closely related to the A-polynomial. So in particular, the boundary slopes of boundary slopes applies to this polynomial. So it is pretty much what we want, and it's related in an explicit enough way that it's sort of meaningful. So basically, in this talk, I'm saying A-polynomial slightly loosely, because Champanica's method is essentially the A-polynomial, but I'm ignoring some technicalities. Okay, so this is sort of the state of play, and that brings us to the work that my supervisors have been doing in the last couple of years. So let me tell you about what I'm calling the Ptolemy method. So this is Josh Howie, and then Dan Mathews, who is my co-supervisor, and Jessica Purcell, who's my main supervisor. And they put a paper about this up on the archive last year. Okay, so what they do is they perform a change of basis on the equations from Champanica's method. And so this was originally done by Dehn. He did this in 2013, but he's coming from a very physicsy perspective, and so that paper just is incredibly hard to read for someone like me. But basically, Howie, Mathews, Purcell do the same change of basis, but then they apply the results in the setting of Dehn filling. So that's sort of the emphasis here. And so when you apply this change of basis to Champanica's equations, you get this new set of equations, and they are Ptolemy-like. So similar to the Ptolemy equations from however many hundreds of years ago that Ptolemy was looking at these quadrilaterals in Euclidean space. So essentially we have these gamma variables. These are related to edges in the triangulation. And then we have these coefficients x, y, z. These are all just monomials in L and M. Okay, and so we get one of these Ptolemy equations per tetrahedron in our triangulation. And so again, this is going to give us a system of polynomial equations. We're going to eliminate all of the gamma variables and be left with something that is a polynomial in L and M. Okay, but the sort of important thing for us is how this behaves when we're considering Dehn filling. So let me talk about Dehn filling for a little bit. Okay, so I'm not going to assume that everyone knows what Dehn filling is, but I'm going to give like a reasonably broad, slightly inaccurate maybe explanation of what Dehn filling is, but anything that I'm sort of covering up is just because we don't need the specifics in this situation. So basically, in our setting, we're interested in Dehn filling a two-component link complement. So take a two-component link, find its complement, and then we're going to fill in one of those components with a solid torus. And so there are infinitely many ways for us to glue in this solid torus, and they all result in different manifolds topologically. So that may be not immediately obvious, but it's a fairly standard result in low-dimensional topology. And basically, details aside, this gives us infinitely many knot complements, which is what we want. Okay, so basically, for our purposes, you can just think of Dehn filling as adding in twists. And so let me show you a picture of what I mean by this. So as an example, we have the Whitehead link. So this is a 2-component link. It's got a purple component and a green component. And we're going to Dehn fill the green component. And basically, if you've never seen this before, just think of sort of chopping along that green component and then twisting. So we sort of chop our 2 strands that go through the green component, and then we just twist them and glue them up again. And so you can add in as many twists as you like with the Dehn filling. Okay, so then we want to do this in a triangulated link complement. So we'll have a triangulation of our link complement, and then we want to perform this Dehn filling by gluing in what we call a layered solid torus. So basically, think of a layered solid torus as just a solid torus that we've built out of tetrahedra, and each of these tetrahedra corresponds to one layer of the layered solid torus. And essentially, you can think of each layer, each tetrahedron in the layered solid torus as adding one of these twists. Now remember, we get one Ptolemy equation per tetrahedron. So one Ptolemy equation per tetrahedron, one tetrahedron per twist. So we get an extra Ptolemy equation for each twist. So using this Ptolemy method, what we have is that the A-polynomial is defined by this set of equations. So we have the Ptolemy equations that we got from the unfilled link, and then we performed Dehn filling, where we put in one extra tetrahedron per twist, which corresponds to one extra Ptolemy equation each time. And so this set of equations is now going to be used to define the A-polynomial. Okay, so this is very nice. And basically, it's feeling fairly recursive. And so this is the sort of behavior that we're playing on here. So Howie, Mathews and Purcell also showed that the Ptolemy equations that come from the Dehn filling are actually really simple. So we don't even have L's or M's in those equations. So they are just the gamma variables. And in fact, so I've mentioned in my abstract something about cluster algebras, and I'm not talking heaps about them today, but this is where the cluster algebra connection is made. So the Ptolemy-like equations corresponding to the Dehn filling are kind of like exchange relations in a cluster algebra. And I don't think I'll say much more than that. If those words mean anything to you, then great, but otherwise, don't worry, they're just buzzwords.
About 5 more minutes.
Sure. So then where I come in is this set of equations that come from Dehn filling, you can actually collapse them into a single equation. So let me tell you more about that. So let's suppose we have a family of knots that are obtained by Dehn filling. So plugging in a solid torus into one component of a 2-component link. And we're going to introduce n twists. So we know that our A-polynomial is defined by finitely many of these Ptolemy equations coming from the unfilled link, and then n equations coming from the tetrahedra in our layered solid torus that are performing the Dehn filling. So okay, so my result is that we can collapse these equations into a single equation. So all of the equations from the Dehn filling, you can collapse into one given by an explicit formula, which I'm not going to show you because it's not particularly enlightening, but it depends only on n, and this equation is going to be in only 3 of the gamma variables. Now, with all of the equations that came from the unfilled link, we can express these 3 gamma variables entirely in terms of L and M. And so once we've done that, we can plug those variables back into this single equation. And what we have is essentially a formula for the A-polynomials of all of those knots that are obtained by Dehn filling that link. And so basically this is incredibly general and applies to any family of knots that come from Dehn filling one component of a 2-component link. And what's particularly nice is we've sort of bypassed a lot of the problems that we had with solving these systems of equations, because all we have to do now is solve sort of the unfilled link equations. So if there are lots of tetrahedra in the unfilled link, we still have a problem, but we've reduced the issue to just those, the equations from the unfilled link. Because once we can solve that, then we can just do this for infinitely many knots. We have an entire family of knots just using this one equation. So I think I will stop there.
Thank you so much. Does anyone briefly have some questions? We have a little bit of time for questions before Rowan starts. Okay. In the chat, could you provide an example of a knot whose A polynomial we can now compute by using your theorem, which was not known before?
Mm-hmm. So there's a link called the Whitehead sister link. So not the Whitehead link, but it's actually the -238 Purcell link. And so you can Dehn fill one of the components of that link, and you get this family of knots, and they turn out to be a lot of the knots are from the sort of census that has been built up. So you get like K73, K83, K74 and K84, I think, knots that are like that my result applies to. So Mark Culler's website has A polynomials for K73 and K74, but not for K83 and K84. So this one covers those. And then basically, like after that point, when you keep adding twists in that Whitehead sister link, you get all these knot complements that aren't even named. So they haven't really been defined by anything, let alone have their A polynomials. So yeah.
Cool. Another question is, does this give an explicit recursion at the level of A polynomials or just at the level of the underlying equations?
Yeah, so it's definitely in the underlying equations, and at the level of A polynomials is something that I'm sort of exploring at the moment. So yeah, I'm kind of optimistic that there is some nice recursive behavior in the A polynomials themselves. Yeah.
Cool. Well, if there's no further questions, thank Emily once again. Thank you so much. And then do we want to jump straight into Rowan, or do people want a quick 2-minute break to go and make a cup of tea or something?
Can we have a 5-minute break for tea/bathroom?
Yep, we can have a quick 5-minute break. I will mostly stay here so I don't abandon the post, but I will also stop the recording then when I find said button.